So now we return to our picture of the cove and the light spreading out from a point. And we said that this phenomenon is called diffraction. So now we're going to look at this in a little bit more detail. So here we have Huygens principle again. So on the left, figure A, we have parallel plane wavefronts coming in from the left, as if they were rays of light coming in from a certain direction, and they hit an obstacle, and they start to bend around the obstacle and to spread out. But the part of the wavefront that did not hit the obstacle just marches on unimpeded. Now we move to figure B, where there is, instead of just a single obstacle, there's a large aperture. There's basically two obstacles and the waves pass between, and we see that wherever the light passes close to the obstacle, it starts spreading out. So this happens on both sides of the obstacle. But in the middle, where the light did not touch the obstacle, it's unimpeded and it marches out undisturbed. Now if we make the aperture smaller and smaller and smaller, we see that this undisturbed region gets smaller and smaller, and the disturbed region gets larger and larger, until when the size of the aperture becomes comparable to the length of the waves, the wavelength, which in this case is the distance between the successive peaks of the wave. We see here the size of this aperture is the same as the wavelength. We see that at that point, suddenly there is no undisturbed region and the entire wavefront appears to spread out from that point. And so when the aperture becomes the same as the wavelength or even smaller, all information about where the waves originally came from is completely lost. And so we're going to look at this lecture and next lecture, because it turns out that whenever light passes through a hole, this phenomenon occurs. So when light passes into your eye, it passes through your iris, that little hole, the pupil, and if the pupil of your eye would be made very, very small, all information about where the light rays had come from would be lost, and you would just see a blurry view. Now, of course, we see a nice sharp view, so our eyes must be in a regime somewhat like figure B, where the aperture is large compared to the wavelength, because if the aperture was small compared to the wavelength, we would just see a blurry view, no matter how we tried to focus. So long ago, this was noticed by one Thomas Young, an English physicist, and he concocted a very bizarre experiment to explore this in more detail. So he was interested in what the relationship was between how the waves went through those apertures, how they recombined, how Huygens' principle could be used to understand how the light coming from different places interfered with itself in order to produce either a sharp view or a blurry view. And so Young's experiment is called the double slit experiment. So he understood, if we look in the previous picture, that the place where the interference was coming from were the edges of the slit, of the opening. And so he said, well, if I just fill in the middle and just have two openings with disturbed waves coming from both of them, and I see how that light gets put back together, I might be able to understand something about how all this works. So that's why we have two slits in this picture and not one. So Young kind of imagined that each slit is representing the edges of a larger slit. And as we'll see, this phenomenon does indeed apply to any opening, no matter what shape it is. So he wanted to know, if he filled in the middle of the opening and just looked at the light, the disturbed light coming from the two edges of the opening, what would the result be? Would he see two sharp spots? And that's what he expected to see. But instead, he was very surprised to see something completely different. Instead, he saw one bright image in the middle and a whole pattern of equally spaced bright bands on either side. And so these in the terminology of physics are called the bright fringes, and the middle one is called the central maximum, because it's where the most light ends up falling. And so we can see from this that light does something really, really, really strange. It doesn't just project in the way that you think it would. Instead, the wavefronts coming through the different slits interfere with one another to create this pattern that would not be expected. And so here's Huygens' principle again being used to try and explain this. So here we have rays of light coming in parallel from the left, which we can think of as wavefronts, the blue vertical lines marching towards the screen with the holes in it. Slit 1 and slit 2. Each slit is small, so that it's small compared to the wavelengths. We see that the size of the opening is small compared to the distance between the crests of the wave, which means that each slit will act as a single point where waves just spread out from, and all information about their original direction is lost. So here we have our waves spreading out, spreading out, spreading out from the first slit, our waves spreading out from the second slit, and we see that in the middle they cross over one another. And wherever two wave crests meet, there will be a higher amount of light, there'll be a greater intensity. Wherever two wave troughs meet, there'll be a much lower intensity. So this phenomenon is constructive and destructive interference. And so on the screen in the background, there should be an interference pattern And if we look at this line down the middle where the wave crests are touching each other, we should see a bright spot. This is where a lot of light should land. But there will be other spots we could pick on here, which always correspond to wave troughs intercepting one another. And those should be places that are completely dark and there will be no light. So we're going to try and demonstrate this in the next lecture, or you can go on YouTube and look for Young's double slit, and you'll find lots of people who upload pictures of what this looks like and videos of them doing the experiment. So we're just going to briefly look at the idea of interference and the theory of superposition, which is the idea if you put two waves on top of each other, they will produce various different intensities. So here's a very simple way of looking at it. We imagine waveform A consists of these two blips, and waveform B consists of these two other blips. If we were just to put waveform A and add it to waveform B, which of the four following would be the resulting waveform? So pick one. So here we have it. So evidently the answer is 3. At certain times we have one blip only, so we've got, that's the height there, and then just in this part here we've got no blips, so there's nothing. And then in the next period we've got the blip from waveform B, then we have a period where there's no blips at all, then we have a period when there's one, then we have a period when there's two blips turned on at the same time, so we have a greater intensity, and so on. So this is what we imagine is happening at the screen in the double slit experiment. There'll be some places where the light, the positive going peaks from one set of diffracted rings will hit the positive going peaks from the other set of diffraction rings and will result in bright spots. There'll be other places where the troughs meet up and there'll be dark spots. So here we have it for two different waves. So these waves are out of phase by a certain amount. And so the question now is, what is the phase relation between these two sets of waves? Okay, so they were out of phase by 90 degrees. And if we were to imagine the superposition of these waves, we could imagine that at some points the troughs would almost match up, and at some points the positive parts would almost completely match up. And so if we were to add these two waveforms together, we would end up with some interesting pattern. So here is the same kind of thing happening in 2 dimensions. This is a real photograph this time of water waves entering a more complicated cove with rocks and so forth. And so we see that in this aperture here there's a set of diffracted rings spreading out. In this aperture over here there's a set of diffracted rings spreading out. And in between we see these interference patterns. And if you were to go and stand on the beach at different places, you'd probably find waves lapping the shore, or no waves at all. You might see mounds of rocks, mounds of sand, shells in different places, and those would correspond to the interference pattern being projected by the waves as they come in. So you can go to the beach any time and see this phenomenon. When you walk along and you see different piles of shells in different places, it's probably interference that has put those piles of shells in the places that they are in. So it's not just light. So here's another demonstration with light. So here, this is Young's double slits experiment. So in this example, a laser was shone through a piece of paper with 2 very small holes in it. The 2 small holes were quite close together, but instead of seeing 2 spots like Young expected, we see one bright spot in the middle and flanking it on either side of these equally spaced spots, which are the fringes. So in the time of Young, lasers didn't exist, so Young had to use a very, 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 very faint light bulb and be in a very, very dark room, and I'm sure it was extremely difficult to actually see this phenomenon. So the reason you have to use one single source of light and not 2 sources of light is that in order for the light to arrive in phase, it has to have come from the same place. And so you can't use 2 lights and shine them through your 2 different holes, because the waves won't be in phase with each other, as we saw in the previous concept question. So in order to be in phase, they have to come from the same place. They have to have been the same wavefront at some point. So it turns out that lasers are such a case, so that's why we usually use lasers for this kind of experiment. It's much more difficult with other sources of light that are not what's called coherent. So if you do have a coherent light source like a laser, one of the even more bizarre effects is you can turn the intensity down and make it so faint that only one photon of light passes through the experiment at a time, and the interference pattern still builds up over time if you use a very, very long exposure photograph. So this is actually one of the foundational experiments of quantum theory, which tries to explain some of these very strange effects that happen in the microscopic realm. So now it's been demonstrated in the late 20th century and 21st century that diffraction and interference don't just occur for water waves and light and radio waves and all those other things. They even occur for beams of electrons and atoms and even molecules. And so you really can try this experiment at home. It really is super easy. All you need is a laser pointer and some paper and poke some holes in it and see if you can make your own interference patterns. Or again, check out YouTube. Lots of other people have tried it, so you can see how their examples showed up. So now we're going to have to do some math. So the interference occurs because each point on the screen is not the same distance from both slits. So here's the screen with the slits in it. Here's our waves coming from the same wave source in the distance, coming in parallel. They come in phase, they go through the two slits, and then to reach a point on the screen, say this point right between them in the distance, this spot is equally distant from both slits, and so if the waves start perfectly in phase, they will remain in phase because they've travelled the same distance as each other. So we can see that here, they arrive in phase, and there'll be a bright spot on the screen, constructive interference. But there'll be some other spots on the screen, so let's just pick one here that happens to correspond to a place where one of the waves has to travel further than the other. Right? The wave from slit number 2 has to travel further than the wave from slit number 1 to reach this point on the screen. And if we pick this point such that that extra distance is exactly one wavelength, the waves will again arrive perfectly in step, and there'll be a bright spot on the screen. But there'll be other spots where this condition isn't met. So let's find a place between the central maximum and this bright interference spot, somewhere in between, and just, say, let's just pick anywhere in between those 2 points and look at it. If we play the same kind of game, we can see that the light from slit number 2 always has to travel further than the light from slit number 1, but unless we pick those special locations, that extra distance won't be exactly one whole wavelength. And if it's not one whole wavelength, we won't get perfect in-step arrival of the waves, and so destructive interference will occur. And in particular, if the path difference, as it's called, this extra distance that one wave has travelled compared to the other, if that extra distance is exactly half a wavelength, the waves will arrive exactly out of phase with each other, and they will undergo perfect destructive interference, and no light at all will arrive at that point on the screen. All the energy goes into the constructive interference spots, and no energy goes into the destructive interference locations. So this explains why Young saw what he saw. So let's look at the geometry of this thing. So the distance between the slits we're going to call d. The difference in path between the two distances from the two slits to a single spot on the screen is called the path difference. And we can see from the geometry of this situation that if this angle in here, the angle to the spot on the screen that we're interested in, say the angle to the first bright spot, is theta. This is the angle by which the light ray appears to have bent. Right, the light ray appears to come in parallel from the left. It appears to bend and follow this path up here, and this angle that it bends by is the angle theta. We can see from the right angles in this situation that angle theta is also this angle in here that makes a right angle triangle with the distance between the slits and the path difference. And so from this, if we look at what is the sine of that angle, the sine of the angle is the opposite over the hypotenuse. The opposite is the path difference. The hypotenuse is the distance between the slits. And so we can say that d sine theta is equal to the path difference. And if the path difference has to equal exactly lambda, then we can say that lambda equals d sine theta. And just like that, we've come up with an equation that describes the angle that a light ray will appear to bend through when it undergoes diffraction by a pair of slits. And so here is the equation written out on the next slide. So d sine theta, which is the path difference, equals lambda. And because we know there are multiple interference spots, we know this condition is satisfied multiple times. So if the path difference equals exactly lambda, we have a bright spot. This is m equals 1. If the path difference equals exactly 2 lambda, m equals 2, then we also have a bright spot because the waves still arrive in phase. And so any integer, any whole number, this will always be true. And so that's why we have this large number of side-by-side bright spots. And we can also look at the condition for destructive interference, which is when the path difference equals exactly half a wavelength. And we can see that the same kind of idea holds there, that if the path difference is 3 times half a wavelength, or 5 times half a wavelength, or 7 times half a wavelength, in fact any odd number times half a wavelength, then this condition will give us destructive interference. So we could also manage making a graph out of this. So if I just quickly loop back to the picture with the laser in it, this one. So here is m equals 0, the incentral maximum. Here's m equals 1, m equals 2, m equals 3, and we see that it's symmetric and it occurs on both sides of the central maximum. So if we drew a line through here, cutting through all of these spots, and imagine a projection plotting, x direction, distance on the screen versus intensity, we would get a graph that looks like this. And so we can again see that if you had some kind of sensor that read that pattern, like a camera sensor or something, and your computer interpreted it and made it into a graph, this is what our graph would look like. And so we see the constructive interference spots at m equals 1, 2, 3, and so forth, and the destructive interference spots exactly equidistant in between those spots. So here's a concept question to think about this. In the double slit experiment, if the wavelength of the light were increased, what would happen to the interference pattern? So the key is to look at our equation, d sine theta, the path difference equals m lambda, and that's the condition for getting bright spots. So if the wavelength of the light gets bigger, but the distance between the slits d stays the same, then the only way for that to happen is for theta to get bigger, which means that the pattern must spread out and the distances between those peaks must get larger and larger as the wavelength gets larger. Okay, so let's do the opposite. If the slits are moved further apart but without changing the wavelength, now what happens to the interference pattern? Don't guess. Think about the equation. So same equation, d sine theta equals m lambda. So if d is increased, but lambda is staying the same, then the only way that's possible is for sine theta to get smaller. So theta must get smaller. So as the slits get further apart, the peaks in the interference pattern get closer together. There's a follow-up question. When would the interference pattern disappear altogether? So we see here that if we make d larger and larger and larger, the interference pattern gets tighter and tighter and tighter, smaller and smaller and smaller. So apparently that must be the answer. Which seems completely counterintuitive, doesn't it? Because it seems like if you had a single slit, which would be the opposite case, if I move the slits closer and closer together, you would expect that when they eventually merged and became one slit, you would just see one spot on the screen. But this equation is not saying that. It's saying that the opposite happens. It's saying that as the slits get closer and closer together, the interference pattern gets wider and wider and wider. And as the slits get closer and closer together, the interference pattern gets wider and wider and wider. And if we was to do the opposite and make the slits further and further apart, the interference pattern would get smaller and smaller and smaller until it would disappear and just be a tiny bright spot. So this is very strange and not what you would expect if you just thought about it without knowing about diffraction and Huygens' principle and young slits and so on. Okay, next one. In a double slit experiment, what path difference have the waves from each slit traveled to give a minimum at the indicated position? So there's the indicated position where the little green arrow is. Okay, so again think about the equation. A bright spot occurs whenever the path difference is equal to one whole wavelength. Starting in the middle, both rays of light have traveled the same distance. For the next fringe, the difference in path is 1 lambda. For the next bright spot, it's 2 lambda. The next bright spot, it's 3 lambda. But we're looking at the next dark spot, so this must be 3.5 lambda. So the answer is 5, more than 3 wavelengths. But it's not just any old amount more, it's exactly 3.5 whole wavelengths, which they've written here as 7/2. Okay, so that concludes today's lecture. So the homework is on all of the material preceding it, and on Wednesday we will pick up where we've left off. and we'll be looking at diffraction gratings and taking some of these ideas to make our own measurements.